Hi there! Welcome to the 21st episode of the Synth project, where we are going to build a synth together. Last time we worked on a prototype of a controller for keyboards, having a single switch for each key. That prototype didn't work very well. In fact, we found 3 problems that needed to be addressed. Let's take a look at a new version of the controller and let's see if this time it does the job. Have fun! After last time's failure, I decided not to reinvent the wheel one more time and do instead some research on the internet to see if I could find something useful to solve my problems. I ended up on the website Music from Outer Space of the late Ray Wilson. It looks like he must have faced similar problems as mine in his design of a keyboard controller, and in the course of a few years he ended up with 2 functioning versions of the keyboard controller. So I decided to study his schematics and see if I could get some ideas to improve my own design. The result is the schematic I will discuss with you today. Here it is. Before saying anything else, please don't bother looking at this part of the circuit on the upper right corner. This part just represents all the bypass capacitors added to the power supply pins of the various ICs, nothing more. Each pin will have its own bypass capacitor connected between that pin and ground. Let's examine the rest now. The first idea that caught my attention is to use a constant current generator to power the array of resistors of the keyboard, instead of using a constant voltage. 2 good improvements come out of that. First, I don't need to care anymore about the number of keys the keyboard is made of. With a constant current, the voltage between the leads of each resistor of the keyboard array is always the same, as long as they all have the same resistance. And that's because the delta V at each resistor depends only on the resistance and the current that flows in it. With a constant voltage, the current would change depending on the number of resistors, and so I would have to make new adjustments whenever I change the number of keys. I can therefore drop the 2 trim pots at the 2 ends of the series of all resistors and use instead one single trim pot to fine-tune just the current. The trim pot can be tuned once and for all with any number of keys. We just need to make sure that the voltage between 12 consecutive resistors is 1 volt, because we know that every octave increases 1 volt the control voltage. Everything else is automatically adjusted, no need to do anything else. The current generator in this new design is a standard design using an op-amp to deal with the negative feedback and a transistor to generate the actual current. Take a look on my video on current generators to see the details of how it works. Here just notice that the generator is made out of U1.2 and Q1, along with a few polarization resistors and a couple of feedback resistors to add a negative feedback to the op-amp to prevent auto oscillations. Trim pot R29 takes care of tuning the current we need for the whole array of resistors, regardless of how long it is. The second improvement may not be obvious, but it is very important. In the case of the constant voltage, if I press 2 keys, I short 2 resistors together, making unpredictable the output control voltage while playing. The result is that strange sounds may be generated. In the case of the constant current, it doesn't matter how many keys I press. The final result will depend always on the lowest key being pressed, and other keys will have no effect. This is actually the solution adopted in the first analog monophonic synthesizers. The CV output only depended on the lowest key being pressed, and that's what we really want to reasonably play a melody with a keyboard. The current generator provides a constant current at the collector of Q1, which is a PNP transistor. I use a PNP transistor to polarize the resistors with the positive and the negative side in the right place. It works the same as the generator demoed in my previous video on current generators, but it is just using a polarization that is just the opposite. The control voltage output from the keyboard enters the circuit at point F, where we have an op-amp used as an impedance adapter or voltage follower. The CV jack on the panel will be connected directly to the output of this op-amp through the connector U4. The network composed by D1, D2 and R6 allows to effectively polarize the beginning of the resistors array in the keyboard, so we can have a proper reference for the CV voltage. Capacitor C5 is there to attenuate adverse effects of bouncing of the keyboard switches contacts. Op-amp U1.3 takes the CV output and amplifies it with a gain of about 4, 3.9 to be exact. We do that to have a signal that is big enough so we can manipulate it while limiting any loss of signal that would cause those changes in amplitude that we were experiencing last time. The philosophy here is to amplify a little bit the signal every time we do some processing on it. And so we will introduce a gain every now and then in the circuit before any major manipulation. And in fact, the signal from this stage is immediately applied to point B of the circuit, where it goes through a high-pass filter made of C12 and R9. We need the high-pass filter to obtain an impulse for each variation of the control voltage. But since the HP filter, the high-pass filter, introduces an attenuation, we first amplify the signal and so we don't lose any of it. Now, before following the signal that generates the trigger pulses, let's take a look at the gate signal circuitry. The same CV that enters point B goes also through U6.2, which is configured as a voltage comparator. The reference voltage is provided on the inverting pin by resistor R21 and diode D5, along with the minus 12 volts from the power supply. Basically, with this combination of components, we will have on pin 2 a reference voltage of minus 0.6 volt. Whenever the CV is greater than that, which means a key is pressed, the op-amp output will go all the way up to about plus 10 volts. Whenever the CV is lower than minus 0.6 volt, and we know it will be that way when no key is pressed, thanks to D1 and D2, the comparator output will go all the way down to about minus 10 volts. Using this comparator, we will avoid another of the issues from last time, the output noise every time a key is pressed. With the comparator, every time a key is pressed, the output will go to plus 10 volts, and whenever no key is pressed, the output will go down to minus 10 volts. These voltages have the same shape as the ones we require for the gate signal. However, the voltages are not a TTL level as they should be per our own requirements. To make them compliant, we now need to remove the negative part and have in its place a 0 volt. In addition, we need to cap the voltage output to plus 5 volts. Op-amp U7.3, along with R28 and the Zener D11, do just that. Whenever the voltage is positive, the Zener will cap it as 5.1 volts. And whenever the voltage is negative, the Zener will behave like a directly polarized diode and will take the voltage to about 0 volts. Op-amp U7.4 will finally adjust the output impedance and provide the actual gate signal to the appropriate jack on the panel through the connector U9. Now we have a clean gate signal every time a key is being pressed. Okay, let's now go back to the HP filter made out of C12 and R9. The filter will generate a pulse on pin 3 of op-amp U5.2 every time there is a change in amplitude of the CV signal. If the CV signal increases, we will have a positive pulse. If it decreases, we will have a negative pulse. So every time there is a change in the key being pressed, we will have a pulse either positive or negative on pin 3. Unfortunately, we will also have a negative pulse when the last key is released, and we don't want that. The rest of the circuit you will see will be used just for that, to detect when to prevent the pulse from being generated at the trigger output, and actually cancel it. And this is the other part of Ray Wilson's circuit that I incorporated in my design. More on that later. Right now, notice that the generated impulse will have an amplitude that is proportional to the change in amplitude of the CV. And this was the last problem of the original design. To make all the pulses of the same amplitude, we just need to amplify them in such a way that they will always saturate the amplifier, so they will all be capped at a value close to the one of the power supply, about plus and minus 10 volts. And this is basically what op-amp U5.2 is doing. It is in fact configured as a voltage amplifier with a gain of about 200, which is more than enough to have at its output only pulses of plus or minus 10 volts. And now, this part is basically identical to the one from the previous design. Since I have pulses that are both positive and negative, I add an inverting amplifier that inverts the voltage of every pulse. Then I use two diodes, D3 and D4, to catch all the positive pulses from the two op-amps U5.2 and U5.5. These are all the pulses present at the HP filter output, but all with a positive amplitude. Resistor R14 and capacitor C14 take care of cleaning the crest of the pulses and make them a little less pointy and more squared, just a little bit, which is just enough for us. So now at pin 10 of U5.3 we have positive pulses every time a key is pressed, and when the last key is released, that too, yes. Problem is, we could have noise along with these pulses like the one we saw in the previous episode, and it is in fact very likely to find it, since this part of the circuit is still the same. No worry though, we can remove the noise the same way we did with the one in the gate signal. We use a comparator to either have a minus 10 volts or a plus 10 volts and nothing else. Any background noise will be brought down to minus 10 volts by the comparator. To make this effective then, we first use another impedance adapter on the output of U5.5. At the same time, we also increase the signal to double its current amplitude, just to make sure that the actual signal is high enough to distinguish it from the noise. This is done through U5.3, which is configured as a voltage amplifier with a gain of 2. The output of this amplifier goes directly into U5.4, which is configured as our comparator. The reference voltage is set by R18 and R19, and provides a voltage of 7.2 volts on pin 13, filtered by C15 to keep it clean. So, every time the voltage of the pulses exceeds 7.2 volts, we will have a comparator output of plus 10 volts, and every time the voltage of the input is less than 7.2 volts, the output voltage will be about minus 10 volts. This way, we can remove any kind of noise up to about 7 volts, and we know that the noise was about 1 volt in amplitude when we tested our previous circuit. So, this should be an effective way of eliminating it. The cleaned pulses going between minus 10 and plus 10 volts are now available at pin 14 of U5.4. But remember, there is still an extra pulse caused by the release of the last key. So we need to manipulate this signal a little bit more to eliminate the extra pulse and let go through only those pulses representing keys being pressed. And that is the purpose of the last part of the circuit, going from input C to the trigger output. Let's see how this last part works. The central point for the elimination of the release pulses is the op-amp U6.4, connected in a configuration that works at the same time as a comparator and as an end port. The end port is made out of D8, D9 and R26. Whenever there is a negative signal on any of the cathodes of D8 and D9, it will bring down the voltage at pin 12 of the op-amp. Only if both signals at the two cathodes are positive, the signal on pin 12 will be actually positive. The reference voltage of this op-amp used as a comparator is of 6 volts, as defined by resistor R23 and R24 and filtered by capacitor C17. All in all, whenever one or both inputs at the diodes are below 6 volts, the output of the op-amp will be about minus 10 volts, and whenever both inputs are above plus 6 volts, the output will be about plus 10 volts. Given that, to remove the release pulse from the trigger output, we need to end all the pulses with a gate signal. As long as the gate signal is high, any pulse will be able to pass through op-amp U6.4, but if the gate is low, the pulses will not pass, and we will have a constant voltage of minus 10 volts at the output of this op-amp. This will eliminate the release pulse, because when that is generated, the gate will be already low, since there is no pressed key. That said, we can use the gate signal at point E and inject it in D9. Then we can take the pulses present on C, invert them, and use them as input for diode D8. And in fact the signal is inverted in U6.5, and then the pulse is manipulated by D7 and R25 to remove the negative part of it and leave only the positive part. Then the new pulse is cleaned by the comparator U6.3. Finally, it is applied to the end port of U6.4. The final signal will work like a pulse going from minus 10 volts to plus 10 volts. Therefore, we need to manipulate it one last time, like we did with the gate signal, to make it look like a TTL signal. And this is done through U7.2, U7.5, R27 and the Zener D10, which make up a circuit identical to the one used for the gate signal. And that should be all. We now need to run new tests in lab to see if this circuit behaves correctly, really eliminating all the issues that we saw in the previous episode. Let's do that right now.
So here is the prototype of the circuit that we want to test. In this area here you can see the constant current generator. Here is the transistors that generate the current, and in this chip contains the 3 op-amps that we are using for this section of the circuit. One that actually controls the transistor itself, and the other 2 that generates the buffering for impedance adaptation of the control voltage generated by the keyboard itself. These cables are those that go toward the keyboard, 1, 2 and 3. One is the one with the current is actually generator, this blue one. This is the ground, and this is the return, basically the point F in the schematic, where we get the control voltage generated by the keyboard and we use it internally in the rest of the circuit. This block here at the end is actually just the group of impedance adapters for both the trigger output and the gate. One is available on this cable and the other one is available on this other cable. And you can notice also the Zener diodes right here, one, and the other one is right here, which are used to cap the signal to the 5 volts necessary to make it work as a TTL signal. The rest of this circuitry here in the central section is the one that works on the control voltage generator over here to extract the pulses for the trigger and also to remove the pulse for the last release of the last key on the keyboard. We saw last time that when you press the key and then you release it, at the moment of the release there is a change in voltage that causes another pulse, and we want to remove that. So this circuit does that. This part here is the first part of the element, the one that generates basically the pulse itself from the control voltage, and then basically let it pass through the first amplifier, which increases the amplitude up to 200 times and basically caps it to the positive of the power supply. And then there is the other element that inverts the level of the signal and brings it basically all the negative signals to positive. And so both of them, they are collected to the diodes here to make the train of pulses that we want to deal with. And then there are also inside here there are the other 2 op-amps that are used to adapt the impedance and act as a buffer, therefore, for the signal coming out of the 2 diodes. And then the other one that makes up the voltage comparator that removes the noise in between the triggers. And then there is the one op-amp that is used as a comparator to remove the noise in between 2 different triggers. This other section over here is actually the one that removes the trigger generated by the key release and eliminates it. And you can see here the 2 diodes. Let me see if I can show them to you. Here the 2 diodes that act as an end port to combine the triggers with the gate signal to remove basically the last trigger which falls outside the range of the gate. So this is the circuit. Now we just need to test it and see if it works. The first thing to do to test this circuit is to tune the current generator so that we can have a difference of voltage between the 2 ends of the key of 1 octave of exactly 1 volt. We just push the first key and we read the voltage. So 1.559, let's round it to 1.56. And then on the other end, we should read 1 volts more. So this is 1.56. We should read here 2.56. Instead we have 2.55. So we have to adjust the input here so that we read the correct value. So again, here is 1.65. So we need to increase this a little bit. So we have to go to 2.65 now. This direction we increase, so we have to go the opposite direction. Still high. Let's go down a little bit more. Okay. 69. 67, 68. Let's check this one again now, because this has moved too. So 1.67 now, and this is 2.68. We have to go down just a touch more, just a little bit, and let's try again. 1.67 and 2.68, still a little bit lower. Try again. 1.63, 1.64 basically, and 2.63. We have gone too low, so we have to increase it now a little bit. And again here 1.66, 2.66. We're done. So that's exactly what we wanted to. And basically this way we should have a difference of 0.08 volts between one key and the next. So this is 1.66 and this is 1.74, 1.84, 1.93, 202, 3 diamond. You see, it keeps increasing for even deltas until we reach the top value, which is exactly 1 volt away from the previous. So here we have 166 and here we have 266. So the current generator is tuned, so now we know for sure that these keys will generate when pressed the correct control voltage, and now we can see how the rest of the circuit works. Okay, so let's test the circuit. I have connected both probes of my oscilloscope, one on the trigger and one on the gate, so we can see both of them at the same time. And later on we'll also check the control voltage. But for now let's concentrate on the triggers, which were the root of all the problems the last time. So let's start with simple tests, like a single key pressed. And you can see that as long as I keep a key pressed, there is only one trigger and then a continuous gate. And then when I release the key, the gate goes down. And you can see there is no noise this time. You remember the noise that we found in the previous video, but right now there is none. So everything is very clean, as you can see. And now let me show you what happens with multiple keys. If I press a lower key and then an upper key, see, this key doesn't do anything because this one, the one on the left, takes precedence. But if I keep pressing it and then I release the other one, here's the spike of the trigger for the new key, which means has been selected. Only where I release all the keys, then the gate goes away. Let me do it again. Left key, right key. You see, when I release the left key, there is the trigger for the left key, and then the gate continues until I release the last key, and then it goes down, and there is no further trigger. So triggers are there only once for each key, as you can see, and so we don't have any more the triggers, the pulses, for the release of the buttons. So now it works correctly, finally. Let's now take a look quickly at the CV output. So let me move around the probes. I will need this one, and we'll only look at the yellow one. And so let's see, let me connect it to ground here, and this is the CV output. Oops, let's do it again. The ground, which I can take from here, and this is the CV out. There we go. So right now there is a slight negative signal, which is fine because we don't want anything. Now if I press a key, here it comes, and now if I press another key, you can see it's higher and higher and higher. And there is a clear difference between the first and the last key. And if I push multiple keys at the same time, see the second key doesn't do anything until I release the first. And then we see the increase over there. Or I can see the decrease if I now push the one on the left, you see? And now I've released everything. And so yeah, this works fine too for all the keys. You can see that they progressively go higher and higher, following the rule that from the first key and the last there is a total of 1 volt of difference. And that's it, everything works fine, so I guess we are done with prototyping and we can now actually build this circuit.
So let's conclude our discussion. We had 3 problems to fix. The first one was the presence of an extra pulse when a key is released. We needed to prevent it from happening because it doesn't tell us that a key has been pressed. It tells us the opposite. That problem has been solved cancelling the extra pulse with a discrete logic gate. The second problem was the amplitude of the pulses. When playing legato, keys that are close to each other generate smaller pulses than those that are far away. That problem was solved by calibrating the amplification of the signal in the various stages of the controller. The third problem was the noise accompanying the pulses, both for the gate and the trigger signals. We eliminated the problem by designing the critical part to avoid auto-oscillations, and by keeping a high-level signal until the last moment, when it was reduced to a TTL level, reducing at the same time any residual noise. It looks like the design is now fine and responds well to the lab tests, even when using the noisy switches of the mini keyboard, which are really not reliable. I therefore ordered the PCB for it to my supplier, and in the next video we will build the actual module, test it, tune it, and install it in the Synth rack. If you don't want to miss the next episode and any other future episode, you may want to subscribe to the channel and enable the notification by clicking on the bell. In the meantime, I'll see you soon, and as usual, happy experiments!